So when we want to analyze the structure, uh, we have to uh, get a mathematical model of the mathematical model, and that is known as a governing equation of the structure. So what happens is governing equations are generally partial differential equations for our structures of different orders depending upon the problems which we solve. So these PDEs are uh, sometimes difficult to solve, difficult to solve analytically. Means like I cannot just integrate the PDE and get the solution because integration is not possible for complex domains. Integration is difficult for complex domains. So approximate ways of obtaining solutions. And in that, one method is finite element. So easily used within the computer. The computer can easily give us a finite element solution, which is approximate. So this is the goal of our course. Like we want to analyze the structure. So obviously, if I want to analyze the structure, I have to get a governing equation, and then I have to solve it. So if I want to solve it, it is not always possible to just directly integrate. So I have to resort to numerical ways of integrating. So in that, one method is finite element. So finite element method is like easily programmable in computers, and we can solve different complex problems which we want to solve. So we have seen till week 4, we have seen 1D structures. 1D structures. So those are bar and beam problems. So those two are 1D structures. So we saw how we can use finite element method and analyze those structures, like various bar and B problems we have looked at. So how we choose the integrating polynomial and all those things we have learned till before. So in week 5, we are entering into a more general case, a more general case, 3D domains. So any structure, uh, like whatever is there, uh, even a small beam is a like is in general a 3D structure, but because the length is more than this breadth and the depth of the beam, so we idealize it as a 1D structure. Idealize it as a 1D structure and solve it. But in general, this is a three-dimensional system. or a three-dimensional structure because it has length, breadth, and width. But length is very large compared to the breadth and depth. So that's why we can idealize it as a 1D structure. Similarly, in future lectures, we will also talk about plates. So plates are also like this. Any plate, uh, you can look at this. This is a plate. So this shaded part is the thickness of the plate. So compared to the length and breadth, depth or the thickness of the plate is very less. So you can idealize it, like we can idealize it as a 2D structure, idealized as a 2D structure, and we solve it. Idealize that as a 2D uh, structure and we solve. So this is how we do. This is how we have gone towards uh, solving 1D bar problems, like 1D bar and 1D beam problem. So we have idealized the structure as a one-dimensional structure, and we have solved. But in general, any structure is a 3D element. So if I have any 3D structure, like let's say like some complex 3D body is there, like this, uh, something like this. This is a three-dimensional. Like let's say you can say this is a rock. Okay. So if I take 3D 3D body or 3D structure, you can say. Now, if I take a small infinitesimal element in this, okay, small element, small element, a cubic element, and if I zoom this, okay, and if I zoom this is a small element at one point. Let's say at one point on the body, at one point in the body, 3D body. So that small point, if I zoom it, it will look like this. So its dimensions are, let's say, dx and dy and dz. So it's like very, very small, but I'm just zooming it for visual purpose. So this is, let's say, this is somewhere in the middle of the body, in the middle of the rock. I am taking an element. So, so obviously, if I am acting some kind of load on this, if I'm applying some kind of load on this rock, and some load is acting on this rod, it will be stressed, like because uh, it has to transmit that load and it has to take that load, and it will undergo some deformation. And that's like due to the strains which occur, there is also stresses which will be developed in the body. So uh, if like all the body will have different stresses on all the surfaces. Uh, let's say this is x plane, here sigma xx will be there, and here uh, uh, sigma zz will be there here, and here we will have sigma yy. So these stresses will be there, and also we will have the shear stresses. uh, at each point there will be like something, here you will have, this is an uh, this is xy plane. So I will have sorry, this is the xz plane. So I will have xy, sorry, xy, tau xy, and tau ix. Here stresses will be there. Here, this is the zy plane, or you can say uh, this is also a similar kind of xy plane only. So we will have tau yz, tau yx, and here tau uh, yz. Here this is tau yz, and this is tau xy. Okay, yeah. So there will be different stresses acting on this infinitesimal element. So if I'll draw it clearly, if I have, let's say, an element like this, here, let's say, I'll draw whatever is given in the notes, make the change of coordinates. So let's say this is x, this is y, and this is z. So here, if you have in y direction, let's say you have sigma yy, and you will have sigma yx shear stress, sigma yx, and in this direction you will have sigma xz. Y, yeah, sigma yz. Now, as I go from this plane at the this plane, when I say this plane, this plane, as I go from this plane to this plane, there will be some change, right? There will be some change. Uh, there will be some change in the stresses because this is a different plane and that is a different plane. Here it will be sigma yy plus something like you can say d sigma yy by dy into delta y, or you can say dy only. So similarly, stresses will also have some change when we go from here to here. So similarly, in x and y directions also uh, we will have this all this in all these planes. In all the planes, we will have some stresses. So this is a small block in the body. So we know that every point on the body should be in equilibrium. So that is what we have learned. Force equilibrium should be there. Uh, at least for the static problems, like when we go into dynamics, we will see there is something called dynamic equilibrium. So that is a different case. But here, force equilibrium should be satisfied. So in order to satisfy force equilibrium, we have to make all the forces in x direction is equals to zero, all the forces in y direction is equals to zero, and all the forces in z direction should become zero. So if I take this like for that I have to take this this is a stress and this is an area. So all the stresses and all the areas in the x direction, all the stresses in the x direction should be taken, and I have to calculate all the sum of them, and it should become zero. So if I do that, like let's say I'll just write for sigma xx for xy. So that will be sigma xx plus delta sigma xx. Delta x sigma xx is nothing but dx sigma xx by dx into dx. This is the total stress on this plane, let's say. This is the total stress on this plane. Into the area, I can write it as this is the plane, and this area is dx into dy. So to stress on the plane into area, or I will write it as uh, yeah, I'll write it as dx into dy. Okay, minus if I am taking here, if I also have forces in the x direction here also on the top plane. So opposite plane, that will be just sigma xx into uh, this is dy into dz. Yeah, dy into dz. Similarly, there are also shear stresses which are acting. That also we have to take into account. Delta x, delta y minus tau yx into delta x, and sorry, this is delta z. Delta z. And then we have zx also, which is acting in x direction. Delta x, delta y, and tau zx, delta x, uh, delta y. So in addition to these forces, there can also be some body force. Body force may be some kind of magnetic field acting, which will be creating some kind of force. Or you can also say uh, the self weight of the body is there, which is acting. So that those these are body forces. So magnetic field, electric field, those can also generate some kind of force. We have to take care of them also. So that will be equal to, so that will be in force per unit volume. So we have to take Bx1, which is force per unit volume, and multiply with the volume of the element. So volume of this element is delta x, delta y, delta z. So, or you can say dx, dy, dz. So this should be equal to zero for a static case. If this is a dynamic case, then we have this also that we should take care. So rho into delta x, rho into u double dot into delta x, delta y, so but we will ignore this for the time period. There is, assuming that there is no dynamics involved. So this is the static equilibrium condition for x. So all the forces in x should become zero. So if you want to read it, like I have not drawn the diagram clearly. Like if you want to a more detailed explanation, you can take some solid mechanics textbook by LS Srinath, or you can, yeah, LS Srinath's books or someone's book you can check out. Advanced Solid Mechanics text. So similarly, if I take sigma fi is equals to zero, sigma fz is equals to zero. So I will get three equations. Okay, this is first equation. I'll get three equations. So those I can finally write as this sigma xx by dou sigma xx by dou x plus dou tau yx uh, by dou y plus dou tau z by dou z plus fx. Fx is nothing but the body force. I am using or I will just write as dx. Okay, equal to 0. So this is nothing but I am just simplifying this equation. I'm just simplifying this equation. Okay, there is nothing to be worried about this. So I'm just simplifying this equation. So if I simplify this, I'll get this. Okay? So similarly, if I simplify the second equation from sigma f uh, fi is equals to 0, I'll get this. So dy is equals to 0. Similarly, if I simplify the sigma fz is equals to 0, I'll get sigma tau z, right, so y, sigma dou sigma fz by dou z plus fz equals to, or bz is equals to 0. Okay. Here, this is nothing but dou sigma xx by dou x into dx. Okay. Similarly, delta tau y, yx, all this can be written like this. So delta sigma xx is nothing but change in stress that I can write like this. Okay. So these are my three governing equations which I get in a 3D case. So this is the more general case. Okay. So at H, like this is the equilibrium condition that has to be satisfied. And there are also like moment equilibrium conditions, like that if I take the moment equilibrium conditions, like I'll get tau xy is equal tau xz is equals to tau zx, tau xy is equals to tau ix. So this also you can check out using any text if you get time. So this we obtain through moment equilibrium. So force equilibrium, moment equilibrium, everything is taken, and then we get the governing equation. This is the final governing equations for the uh, a more general 3D case. And if I want to, if I want to convert, like I want to make these equations in terms of displacements, right? Like so, whatever we have seen, the bar problem, beam problem. So there we have replaced stresses using the constitutive relation, and we have made the final partial differential equation in terms of the displacement. So then we will solve it. So I want these stresses to be replaced by displacement here. This stress terms to be replaced by displacement. So there is some kind of relation between stresses and strain. We know that. So stress for a linear elastic case, this is the stress strain relation. Stress is equals to E into epsilon. So this we have seen. So for a this is for us, let's say for a one-dimensional problem. If I am writing this same thing for a three-dimensional problem, because there are like different in the different direction, like different directions, there are a lot of stresses. Like we have seen shear stresses, normal stresses. So then I can write it like this: d into epsilon. So for an isotropic case, I can isotropic, homogeneous and isotropic case, I can write it like this: sigma yy, sigma zz, and tau xy, and tau yz, and tau zx. Okay. This is also a derivation, like uh, we in general we assume the material is anisotropic and um, anisotropic material, but after making some assumptions about the material, like if I like assuming that Young's modulus is same in all directions and Poisson's ratio is same in all directions in the material. we get an isotropic material. So in general, like materials which we use in engineering, like steel and aluminum, are isotropic material. Like there are also orthotropic materials. Like for example, if you take wood, it will have different in different directions. E will be different. Like in perpendicular directions, E will be different, right? Fibers will be aligned in one direction. In that direction, strength will be more. E will be more, and in the perpendicular direction along which the fiber uh, are uh, aligned, if you apply stress perpendicular to that direction, uh, wood will break easily because strength will be less. So that's why E will be less. So that is an orthotropic case, but we will assume that we are dealing with isotropic case for time being. Uh, if you have, like, let's say composites also, they will have different properties in different directions. So based on the requirement, we design those kind of materials. Okay, so this is a general case. You can read about this in some advanced solid mechanics text. You will get a clear uh, understanding. Like, more importantly, if you read some continuum mechanics text, it will be more easier to understand mathematically. But we won't discuss that here. Just writing the relation. So this is this stress vector sigma is not actually a vector. This is a tensor, but because we have assumed our uh, using this moment equilibrium condition, we have assumed that sigma xx, tau ix and tau yx are equal. So that's why we can write this. We can write it like this. So like a vector, and D is also not a matrix. This is a three-dimensional or a four-dimensional vector. So that you have to read continuum mechanics and all. But this is the constitutive relation. You can see that stresses are related to strains. Stresses are related to strains. So I will substitute this constitutive relation in my governing equations, and I will get the governing equations in terms of the strains, right? So there are also strain displacement relationships. So strain displacement relationship is there. So now from in the governing equations, like the governing equations are in terms of strains. Now I will use the strain displacement relations, and I will substitute them. So these are my strain displacement relations: epsilon xx, epsilon yy, epsilon zz, gamma xy, and gamma yz, gamma z. So this is a differential operator. Y 0 x. Rho by rho z 0, rho by rho. And these are my displacements in u, x, y, and z direction. Assuming that the body is undergoing displacement u in x direction, v in y direction, and w in the z direction. I can also write it as epsilon is equals to this operator L, or some kind of Greek letter. So I can also write it like this. So L is this. Okay. So now if I substitute this in my governing equation, I will get my governing equations in terms of the displacements. So that is what we solve in FEM. So so let's say this is my governing equation. So governing equation, I'm just writing this using this notation. So L is the differential operator. Sigma is the stress vector we have, right? Stress vector. So L transpose into sigma, I'll get plus F. F is nothing but Fx, Fy, Fz vector. So rho into U double dot. U double dot means U U can this U which is not italicized is a vector which contains italicized like X, Y. So this UVW displacements in all the directions X, Y, and Z will be stored in this vector. So these are italicized. This notation, whereas this vector notation is not italicized. Okay. So that is the difference. So this is nothing but all these three vectors will have double differentiation with respect to time. Now, if I use the constitutive relation, I can substitute sigma is equals to d epsilon plus rho u double dot. Now, I also have uh, strain displacement relation. So, strain displacement relation is L into uh, u plus m is equals to rho u double dot. So, finally, I have got my governing differential equations. So, this will have three uh, governing equations in the domain. So domain is nothing but the 3D body or the some kind of structure, 3D structure which we have taken. So at each point on that, this equilibrium condition should be satisfied. So these are my three governing equations in this. Okay. So now what we do, assume we assume in finite element we assume this displacement, we assume some kind of solution, right? So this capital U will have U, V, W italicized. Now I will assume some kind of approximate solution, which is U cap, V cap, and W cap. So obviously, if I am taking approximate solutions, which will be nearly equal to that, this governing equation will have some kind of residual. So that residual is this U cap plus F minus rho U double dot cap. So cap is denoting approximate solution. So governing differential equation is not being satisfied properly. So now we take weighted residual and we can solve this problem. So that is all. Those are all things we have learned in this week. We have not gone detailedly, like we have not solved the full problem yet, but we have seen various things related to this. So we have seen like any 2D body, like any 3D generalized case, we can uh, approximate it to a two-dimensional elastic continuum. So based on some kind of conditions which have to be satisfied, like we have seen in this uh, I have explained you a plate and a beam or a bar problem. So we have assumed them as one-dimensional or two-dimensional structures, like by assuming some kind of conditions. So beam and plate problems are like generally uh, taken out of plane stress criteria. We will see what is plane strain and what is plane stress condition. So let's say if you have a dam, okay. Let's say if we have some kind of long structure like a dam, like a dam be like uh, will be having like very huge length, okay, like in kilometers, like in kilometers. The dam will be having like kilometers or like let's say 1.2 to 2 kilometers. Uh, this wall of dams will be very high, will be having very high length compared to the cross section here. So because of this huge length, what happens is if like let's say there is some kind of displacement. Uh, let's say this cross section is in x and y direction, and this length of the dam is in z direction. Now let's say if there is some change occurring in the z direction, like some displacement or change in dimension is occurring in the z direction. So let's say if I want to calculate epsilon z, that will be equal to like change in length by original length in z direction. But because this length is like very large, this LZ is very large. LZ is very large compared to this delta Z. This I can take epsilon Z is like nearly equal to zero compared to the other stresses like epsilon XX and all these things. Epsilon XX, epsilon YY, epsilon YY, all this like other strains in other direction are high compared to have a greater magnitude compared to the strains in the ZZ direction. So this is the plane strain condition. So plane strain condition. So we will just assume this as a 2D structure and take this section and do the analysis. So that is the plane strain condition. In plane strain condition, we assume all the strains in the Z direction to be zero. So that is the plane strain condition. Like we use it in this kind of cases, like I have explained, like when length is like very large compared to this, uh, this can happen, like plane strain condition. Similarly, there is also another assumption, idealization we can do, which is plane stress idealization. So let's say I have a plate like this. Now you can see in this plate, the thickness is very small. So due to this like small thickness, what happens is the stresses in the ZZ directions, instead of the strains here, we have the stresses becoming zero because of very small uh, dimension in the Z direction. Okay, let's say this is Z direction, thickness is in Z direction. So this is how we can take a 2D continuum idealization of this and solve this problem. So this is the plane stress field in the domain. So I can just take a middle plane of this uh, plate and solve for that, and then I can, like, if I want some kind of analysis, then I can do the post processing. So this is plane stress and plane strain idealization. So in both of these cases, we are converting a 3D case, or we are idealizing a 3D problem to a 2D problem. So 2D problems we are going to see in this week, and also probably in the next week up to a certain extent, how we will solve 2D problems. Like, let's say if I have just kind of a plate, or a dam's cross section like this, now I have to solve and analyze how the displacement is varying in different directions in this two-dimensional area. So that is my goal, or analysis part which I have to do. So now see this. See this uh, case. Like, I have a constitutive matrix for a 3D case. Constitutive matrix is nothing but this matrix which we have seen. Uh, Sigma YY, sigma ZZ, sigma. Sorry, this is tau XY, tau YZ, tau ZX, and this is my constitutive matrix for an isotropic case. Okay. Now, using the assumptions for a, let's say, plane strain case, we will take. Uh, we will see how this constitutive relation uh, changes. Like, if I take this, I will just is epsilon xx, epsilon yy, epsilon z, epsilon xy. This is gamma. Sorry, this is gamma xy, gamma yz, and gamma zx. So this is my constitutive relation for a 3D case for an homogeneous and isotropic material. Now I want to idealize it, use the idealization for plane strain and plane stress conditions, and change and see how this constitutive relation will change. So for plane stress condition, I will just, for plane stress condition, we know that uh, sigma xz, sigma yz, and sigma zz will be equal to zero. That is our assumption. Now these things are zero. All the z components are zero. if I multiply this matrix and take out these components, I will get 0 is equals to uh, E by 1 minus 2 mu 1 plus mu into uh, mu into epsilon xx plus mu into epsilon yy plus mu into, sorry, 1 minus mu into epsilon zz. So this is what I get uh, if I take out this. Now I can rewrite this and I can make epsilon zz equal to like if I send this to right side, I will get e mu minus 1 by 1 minus 2 mu to 1 plus mu epsilon zz I e into 1 minus 2 mu into 1 plus mu into gamma, uh, sorry, mu into epsilon xx into mu into epsilon. I can obviously like divide it and remove this. I will get epsilon xx is equals to mu into epsilon z is equals to mu into epsilon xx plus mu into epsilon yy divided by mu minus 1. So this is my epsilon zz plus epsilon zz. Now, uh, now I have my sigma xx. Let's say I have sigma xx. Sigma xx is nothing but uh, uh, e into e by 1 minus 2 mu 1 plus mu into 1 minus mu into epsilon xx plus mu into epsilon yy plus mu into epsilon zz. Now I can substitute this epsilon zz into this. I will get everything in terms of, I'll just write it. Terms of epsilon. I'll substitute this. I'll get this plus mu into epsilon yy by mu minus 1. This. Now, whatever the xx terms are there, I can epsilon xx and epsilon yy terms are there. I can take them out as common, and I'll get some kind of let's say C11 cap into epsilon xx plus C 1 2 cap into epsilon yy. I'm just writing this C11 and C22. You will get after simplifying this entire. Similarly, we have also sigma yz is equals to 0. So you take sigma yz is equals to 0 from this or tau yz is equals to 0 from this, multiply this and take that and get relation in terms of epsilon yz in terms of the other strain relations, and you substitute that. So by doing so, you will get sigma yz, sigma sigma yy, and also tau xy you will get. So three equations you will get. Finally, finally the 2D constitutive relation for isotropic material in plane stress condition will be given like this. So all the z strain stress components are assumed as 0. That will lead us to this equation, constitutive relation for a plane stress case after doing the simplification. So similarly, we can also do it for a plane strain condition. So there we have to uh, go the other way. So we have to take epsilon zz is equals to 0 and epsilon yz is equals to 0 and epsilon xz is equals to 0. And from the constitutive relations, we have to simplify them. And finally, we will also get this kind of relation, but a different relation, constitutive relation for a plane strain case. So you can do it on your own. So this I have explained, like we have to assume whatever dimensions which we are taking and get the relations, and then we will finally get a constitutive. Now, the most like trickiest part, whenever we have looked at these things, like for a 2D case, we have to compute area integrals. In 1D case, we were just computing the line integral, like we were just integrating with respect to x. But in 2D case, it becomes even more difficult. Uh, so, like we have to define integrating polynomials, interpolating polynomials very carefully. So, the most like there are like lot of elements which can be used for analyzing a 2D structure, and like these two are like some of these two are like uh, common examples which we can use and which we can use as elements. So integrating polynomials, like uh, let's say this is an element. We have a triangular element, and let's say this is I, J, K. So whenever we do FEM, so we assume that at nodes we will have at nodes uh, the the displacements have to be solved, and the interpolating polynomial should exactly uh, be equal to 0 or 1 at these nodes, depending upon the polynomial which you have. So there are ijk nodes. So if there are three nodes, there will be three integrating polynomials. Let's say because this is a two-dimensional case, we will have u and v. At each node, there will be two displacements. So the body will be undergoing deformations in x direction and deformations in y direction. So we can write them as n1 xy, n2 xy, uh, x comma y u2 plus n3 x comma y u3. So these are n1, n2, n3 are my shape function. So this is v. Now the task we have at our hand is we have to find out what is n1, n2, and n3 for these elements. For quadrilateral, we will have n1, n2, n3, and n4. So, so anything like if I want to find out an integrating polynomial, first I have to write a coordinate uh, matrix. So, coordinate matrix for coordinate matrix for a triangle, I can write it like this. So that I will denote it as C, and it will be equal to 1 x1 y1. This is the first point, or you can say I. Uh, uh, Matrix will have three vertices, right? So there will be three quadrants. 1 x2 y2, and the third point will be 1 x3 y3, or the third vertices. So in this case, the first point is 0, so I will substitute x1 y1 0 0. The second point is 2 and 0.5. I'll substitute 2 0.5. And the third point is this 1 comma 2. So I'll substitute this. Now I want to find out the shape function. So shape functions, we have seen the formula for obtaining them for a triangle uh, at any, like, uh, let's say this is a I shape function. I can obtain it as 1 by determinant of C into alpha I beta ix plus gamma I. So where uh, alpha I is xj, xj and yk, and yk minus yj, xk yj. Beta I is yj minus yk, and gamma I is minus xj minus xk. So I know if I want, let's say if I want n1, so n1 of x comma y, I know what is the determinant of C. Uh, if I just take the determinant of this, I'll get the value of determinant of C, that is 3.5. And alpha 1 is nothing but alpha 1 will be equal to x2 y3 x3 y2. Beta 1 will be equal to j. Beta 1 will be equal to uh, y2 minus y3, and gamma 1 will be equal to minus x2 minus x3. So these values are also known because we know the coordinates. I will get n1 is equals to uh, 1 by 3.5 minus 3.5 into x minus. Now, if I want n2 of x comma y, same procedure. I will have alpha 2, alpha 3, and alpha, alpha 2, beta 2, and gamma. So alpha 2 will be nothing but, so because we are starting from, like here you can see this is going from 1, 2, 3, and 3, 2, 1, like this it goes on. So this is a cylindrical order, 1, 2, and 3. Okay. So if I'm starting from 2, I'll go to x3, y1 minus this. I'll go from x1, 3, and y2. I'm starting from this point. So beta 2 will be y3 minus, and gamma 2 will be minus of x3 minus x1. So now if I substitute them, I'll get, because I already know the coordinates, I'll get alpha 2 is equals to x3 is uh, x3 is 1, and y1 is 0, and the x1 is 0. So this will become 0. So alpha 2 will be 0. Beta 2 is y3 minus y1. So y3 is 2 minus y1 is 0. This is beta 2, and gamma 2 will be equal to x3 minus x1. So x3 is 1, and this will be like this. Minus x1 is 0 already. So I will get, uh, if I substitute here, I will get 0 plus 2 into x plus minus 1 into y. So this is my second shape function. Similarly, I can use this procedure. Now I have to get alpha 3, beta 3, and gamma 3. That will be nothing but these three, because we are starting from 3. Now uh, we have to uh, go to 1 now. 1, 2 minus this will again shift 1. So this will be y 3, and this will be y1 minus y2, and this will be x1 minus, because of this rule which we are using, cylindrical rotation of coordinates. Yeah. So this is how we will get shape functions at uh, different shape functions you will get. If you want to evaluate these shape functions at any point within this triangle, you can substitute the coordinates of this point, like x, y, whatever you have, and you will get the answer. So that is, I think, the first question in the assignment. So you have to find out the shape function, and then you have to substitute uh, those uh, coordinate values and get the value of shape function at any point, the given point in the domain. So this is for a triangular element. If we have a quadrilateral element, how can we find out uh, our shape function? Let's see. So for a quadrilateral element, the trickiest part this. So this is my quadrilateral element. Is given. It will have four vertices. So, and the coordinates of these vertices are given minus 0.5 comma 1, 0 comma 0, 1 comma 1, 0.5 comma 1 point. So these are my four vertices, and this is my quadrilateral. Now I want to find out the shape functions for this. So for a quadrilateral element, uh, because there are four nodes, so I have to take basically a linear polynomial, a bilinear polynomial should be taken. Like let's say we have to assume u of x comma y will be something u naught plus a1x plus a2y plus a3x y. Because there are four nodes, there should be four unknowns in the integrating polynomial or the assumption polynomial also. One second.
Hello, sir. You are not audible.
Yeah. So this is the Pascal triangle which we have to use. So we have to choose our polynomial terms for any element based on this Pascal triangle. because the geometric isotropy should be maintained. For a quadrilateral, uh, we have to take uh, four unknowns because there are four nodes. We should have four unknowns in our polynomial. So there should be four terms in the polynomial, and all those terms should be selected based on this Pascal triangle. So for quadrilateral, we will choose one uh, x, y, and in addition to that, we will choose x, y, because simply using one x and y will lead only to three terms. That will be not sufficient for a quadrilateral because there are four nodes. For a triangle, this will be just uh, sufficient. But for a quadrilateral, we have to choose xy also. So I cannot choose x square or y square because this will break the geometric isotropy. So whenever I say geometric isotropy, like if you take one x, y, and x square, you are saying that your assumption, your solution will be quadratic in x direction, but it will not be quadratic in the y direction. So that will not be suitable for our problems which we solve. But if we take xy, we are not saying this will be uh, quadratic in x and quadratic in x or quadratic in y, but it will be, let's say, combinedly quadratic, or equal weightage is given to x and y. So whenever we choose, if you want to choose extra terms, we should go from the middle. So that's why we choose one x, y, and y. So these are the four terms which we use for our quadrilateral. So now I will define the same coordinate matrix. So the coordinate matrix will be C is equals to 1, x1, y1, x1, y1, because we have additionally this term also, and the second term coordinate matrix is nothing but this coefficients which we have here. The second row will be 1 x2 y2, x2 into y2. Similarly, the third point, there are total 4 points. So there will be four x4. So this is my coordinate matrix, and I know what are the coordinates of the vertices which are given here. So I'll just substitute them here. So if I substitute, I will get 1 0 0 0 1 1 1 and 1 1 0.5, and third point is 0.5 1.5. I'll get this as 0.75, and this is minus 0.5 1, and x3 y3 is minus 0.5. So this is my coordinate matrix. So I like u of xy, or let's say I'll take capital U, which will have more, or let's say I'll just not capital U, small u of xy, u of x comma y will be nothing but this, right? Uh, 1 xy comma y into x into y into a naught, a1, a2, a3. So this is the polynomial assumption which we have made. These are the terms which we have used. Now I want to convert this unknown coefficients into the nodal displacements. So that can be done by using this relation. So we have seen in the 1D case also. Now we are seeing the same thing in the 2D case. So whatever the coordinate matrix which we have, uh, that will be inverted. This is 1 and minus 0.5. Inverse into U1, U2, U3, and U4. So now I have got the polynomial in terms of my unknown nodal displacements. So if I multiply these two matrices, I'll get the shape function. So you first you have to get the display. You have to get the inverse of this matrix. After getting the inverse of matrix, you have to multiply with this. Then you will get something like this: n1, n2 x of y, n3 x of y, and n4 x comma y into u1, u2, u3, and u4. So these uh, whatever the terms which you get in this row matrix are our shape functions or the interpolation polynomials. So now, if you want to evaluate the interpolation polynomial at any point, you just substitute the coordinates of that point and you will get the answer. So for a quadrilateral, you will have four interpolating polynomials because there are four unknown nodal displacements which we have to take. So there will be four interpolating polynomials. So for integrating this, maybe I think you if you have some kind of modern scientific calculator, you can integrate this. Uh, Otherwise, you can use MATLAB or Python uh, and do some kind of code, or you can also alternatively you can just search on Google matrix inverse solver or something like that. There will be tools if like people have made some kind of pages. If you just enter the values and tell it to do some kind of operations, you will get the inverse, or you can also find out the determinant. That also you can do, or you can also write your own code and do it. So this is how we can get the interpolation interpolating polynomials. So uh, this is a quadrilateral, and there is also, like we have also seen for the triangle. uh, as we go, I think there are in assignment there are also uh, much more complex problems. I think there is a square, and and also there is a quadrilateral uh, with more nodes. So based on the number of points you have, based on the number of nodes you have in your element, you have to choose terms accordingly from the Pascal triangle and build this interpolating polynomial. So that is a right procedure to go about that. It's not a very complex thing. Like if you know this Pascal triangle, it will solve a lot of problems, and you can choose accordingly and go about it. There is no confusion. There should be no confusion regarding that. And yeah, what all other uh, element problems we have. First is a triangle. Second is a 1 second. Uh, Okay. So I think the third problem is a triangle with six nodes. So again, you have to take six elements, six terms in the polynomial. So you can choose it like all these six terms you can choose, and you can define this coordinate matrix. Six terms should be there. All the six terms can be taken. In the square with nine nodes, we have to also take this. Uh, there will be extra terms from the Pascal triangle, which you should be uh, we should take x square y square x z. This is x square y, and this is y square x, and y cube. This all these terms should be taken because there are nine nodes in that square. We have to take this. There are nine or nine. Yeah, one, two, three, four, five, six. These are six, and yeah, you have to. Uh, we cannot choose this or this, but we can choose this other. Uh, we will have x power 4 x cube y, and x square y square xy cube and y4. So we have to choose this nine terms for a square with nine nodes. Okay. See, that's how we go about building these interpolating polynomials for our elements, finite elements of different shapes, quadrilateral, uh, triangle, and a square. Depending upon the number of nodes we have to take this Pascal triangle and do things accordingly. And in the assignment, yeah, plane stress, plane strain, and yeah, the other problems are like straightforward only, straightforward questions. You can just uh, submit them. It's not difficult to do them. Yeah. In next week, we will go deeper into how we can formulate this finite element, and we will also see some example problems for this studio idealizations for plane stress and plane strain cases, and some more details about the elements. Like we have not seen uh, more elements. We like although questions were asked about square and quadrilateral in the assignment, but in this week we have not discussed the quadrilateral elements, and there is something called as uh, 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 serendipity element. So different kinds of elements are there. Those are yet to be discussed. So which will be discussed in the next week, and also some problems will be solved for finite element. So as this course goes deeper, like it's like it becomes very difficult to solve problems with hand. So I would suggest you to learn some kind of coding. uh, it's not very difficult. Like you can take some course if you don't know. Like if you already know, that is a good thing. If you don't know coding, uh, you can learn Python or MATLAB, and uh, and start coding problems. So that will give uh, good idea to you on how to go about uh, solving them. Like you will know how computer solves them. So what happens is whenever we use abacus, and let's say we use abacus or ANSYS, and we define, like you take a structure or a machine, you just mesh it and formulate the elements, and you just tell abacus to solve it, and it will give you some result. But what happens in the background is, like in the behind the user interface is very important for us as mechanical engineers or civil engineers who analyze them. Like we cannot blindly rely on the analysis of abacus or ANSYS. We should be able to interpret the results, and we should know how it is solving. So it is just a helping tool, but we have to use this tool by understanding how it works. So blindly, if I am doing something like if I mesh something and if I solve it, I might not know. Like if I have done a small mistake in giving some condition, Abacus will give me uh, some solution which will not be correct, and then we will be in trouble. And like you might have to, like whatever the structure which you are designing or analyzing might fail because of our ignorance. So that should not be the case. We should know how we are solving these finite element problems in using any kind of software. We should have some basic knowledge. Obviously, it becomes difficult when you go to 2D and 3D. That's why I suggest you to learn coding and code one or two problems like throughout this course. Uh, Assume that you are doing some kind of project and take some kind of problem, beam problem, or a two-dimensional plate or something, and code entirely from beginning to end, and solve the entire problem. Like take lot of elements, also write code for assembly, how you are going to assemble those elements, and finally after assembling these elements, solve for the nodal displacements, and then get the displacement over the entire domain. So these things I would suggest you to learn. Otherwise, like you are just if you are just going through the lectures, you won't understand a lot, because finite element is like more about doing and learning, uh, which should be complemented with our teaching in the class. Uh, that is not just sufficient. So we have to solve problems. Then only we will get true understanding of it. Like it's a big ocean, I would say. Like as you learn more, you will get you will get to know more and more things about finite element. But like we have to try our best and learn. So that's what I would suggest. Do we have any questions? Like uh, uh, I will stop early today because I have to go somewhere. Do you have any questions?
Hello, sir.
No,
Hello, sir.
no
Sir,
question. Yeah,
can you
yeah.
explain that for quadrilateral once more. That how to find the
How to find
interpolation
the
function.
interpolation function? Okay. Where do you have the doubt here? Uh,
Sir,
uh,
first we write the constitutive matrix, right?
uh, Coordinate
And
matrix. Yeah. Uh,
sorry. Yeah, after that, I think the equation is that first we have to find the A0, A1, A2. For that purpose, we are doing C inverse into U, right?
yeah, yeah. C
So
inverse into
getting
U.
that
A zero. Yeah, yeah.
so that U
So
what like how will like which what should be used U1 U2 then?
U1, U2, U3 is our nodal displacements. No. This quadrilateral is there. Quadrilateral which I have. Let's say this is node 1, node 2. This is node 1, node 2, node 3, and node 4. Okay. This will have nodal displacements of U1, V1, U2, V2, U3, V3, and U4, V4. So in finite element, we solve for this only, right? What is U1, what is U2, uh, what is U3, and what is U4. So whenever we like initially when we take this polynomial, we assume this polynomial. These constants don't have any meaning, right? So these constants don't have any meaning. A0, A1, A2, A3. These are not representing anything. So I have to reframe this, like I have to reframe the constants in such a way that they represent the nodal displacements. So nodal displacements are this U1, U2, U3, and U4. Because I am taking U here, these are my nodal displacements U1, U2, U3, U4. Uh, did you understand, or should I explain it more?
Yeah, sir. For finding the answer for this assignment
Finding the
question.
answer.
So that
Finding the
time,
answer for this assignment question, right?
yeah,
Mm.
that time we will represent like this, right?
Uh, for finding the problem,
That
for finding the answer for the assignment solution, you don't need U1, U2, U3. Okay.
yeah, no need. So in that case,
You
that we should
you you have. I'll tell you what you have to do in the assignment. You should find out what is N1, what is N2, what is N3, and what is N4. Okay. You will get some kind of polynomial in XY. Okay.
yes,
Like what I'm getting here, N1, N2, N3, N1, N2, N3. In this, some point is given in the assignment, right? Point and its coordinates are given, XY coordinates. You substitute those coordinates and you will get some answer in this N1, N2, N3. So those uh, values you should give in the assignment.
yeah, sir. But that was three-noted element, right? So in that we
Yeah.
had equation for
Hmm.
alpha, beta, and gamma. That xi, like we had ready-made
Yeah,
equations.
yeah,
So in this
yeah, yeah.
case, the first
In this
for
case,
finding
yeah.
which step is coming.
In this case, we don't have that general formula. As I said, you should take the inverse of this matrix. Take the inverse of this matrix. Okay, coordinate matrix,
Yes.
and multiply with this. Okay,
Okay.
multiply with this matrix. Hmm.
So we will get that one row. Each
Yeah,
element will be the function.
each element will be one function. Each element will be one interpolating function. So you will get this is a see this is a 1 by 4 matrix, and this is a 4 cross 4 matrix. If I multiply it, uh, yeah, there is one column and sorry, one row and 4 columns, and this has 4 columns. Yeah, I will get a 1 by 4 matrix. 1 by 4 matrix I'll get, right? I'll get a row matrix like this. So in that first element will be my first shape function, second element will be second shape function, and third element will be third, and fourth will be fourth shape function. Right? Ultimately, if I multiply this, I should get, if I multiply this and this, I'll get n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, right? But I want only n1, n2, n3, and n4 here. They are asking the interpolating polynomial values at some given point. Okay.
Yes.
Okay.
Okay.
We will solve for this u1, u2, u3, like when we define the finite element, when we do assembly and we finally solve the problem, then we will get u1, u2, u3. But for now, these are not required, u1, u2, u3. We are just learning about elements and shape functions. So this is a general, you can use the same procedure for triangle also. Instead of using this formula, you you can do same kind of stuff. You can do same kind of, like, you can take this instead of taking for triangle, instead of 1 xy and xy, I will have 1 xy, and I will, instead of this 4 by 4 matrix, I'll have a 3 by 3 matrix. I invert this and multiply with 1 xy, I'll get the shape functions. Like that formula is just a generalization of this. Okay, you can do, you can use the same procedure. That will be more easier to do. Uh, Instead of like getting confused with that formula, 1, 2, 2, 3, 3, 4, like that. Okay.
Okay, sir.
Okay. Any other questions?
So just one question. I mean, from exam point of view,
Yeah.
uh, do we get such questions in exam, like working out the solution and then entering in the box, or it will be just like objective type, like A, B, C, D type, and answers will be given?
No, you
Any
will get
idea?
both. You will get both kind of questions. You will get answers which have to be entered, and you will also get options also. I think, I don't know the, like, how many questions you will get where you have to type the answer and submit. But both kind of questions will be there, entering the answer.
Okay,
But
okay,
like if your answer is like approximately correct, there will be a range. Like like don't they won't expect you to give the exact point decimal answer. But if it is like approximately equal, there will be a range. Let's say if your answer is 1001, there will be a range from 990 to 1010 or 1020, like that.
okay. Thank
Yeah.
you.
Okay. Any other questions? Okay. If there are no questions, we'll stop it for today. I have some other things to do today. Sorry. Uh, we'll meet next week with more deep dive into two-dimensional analysis using finite elements. We'll all we will see other things, related to that. Like triangular elements were the more focus for this week, but we'll go deeper into quadrilateral elements and square with more nodes and how we can use the shape functions, all these details. And finally, we will solve some problems also. So, and also local coordinates is something which we haven't talked because which it was not asked in the assignment, but that is also a important thing. Local coordinates uh, that also will be looked will be discussed in the next week. So, okay. Hope uh, you are getting something out of this course and these sessions. If you have any questions, you can like anytime email me. I will try to help you in any possible way I can. Okay. Okay. Today we'll stop for now. Uh, Thanks for joining, guys. Have a good night.
Thank you, sir.
Thank you.